Hey, what's going on, folks? It's Mike here, and welcome to your third day in the C programming language. I hope you've enjoyed days 1 and 2, and if you haven't seen those, please go ahead and check those out in the playlist previous to this lesson. Otherwise, if you're jumping right in or following along in the series, today's topic is about memory. So, since we're using the C programming language, it's considered a sort of low-level or mid-level programming language. That is, we're not writing pure machine code, ones and zeros, but we're sort of abstracted on top of that. But we're not quite at the level where we're using a scripting language like JavaScript or Python, which takes care of a lot of these sort of details about the machine for us. As C programmers, we do have to think about things like memory. So that's what we're talking about today. And this is actually one of the fun parts of the C language, or at least a part that we can appreciate when using other languages, that we have this control over how memory is allocated and used. So with that said, let's go ahead and jump into the whiteboard and get a little introduction to what memory is, and then we're going to be talking about some concepts like stack memory, heap memory, and see why that all is important. All right, so memory in general. The way that we can think about memory is just as this giant linear array here. So depending on what kind of machine you're using, you have maybe different amounts of memory. And usually we think about this as our working memory most of the time, but this could be memory like a hard drive, for instance, or a flash drive. Those are all areas where we have storage and can remember things. That's where memory comes from. But for now, let's just think about RAM. And RAM are those little green sticks that you've put into your machine, and that's really your working memory. If you haven't seen those, it might be interesting just to Google now RAM, specifically DDR RAM, and see what your working memory actually physically looks like in your machine. So that said, the actual idea here is, well, we have memory addresses, and I'm just going to label them starting from, say, 0 and growing up to some reasonable number and on and on and on. But this is where you're actually storing your variables. So for example, if I create something like char a, which is a character, and let's go ahead and assign it some value, initialize it, that takes 1 byte of storage somewhere in our memory. So somewhere we have this value stored, whether the actual literal character or the integer representation of it in memory. And then if we create some other variable here, like an integer, and I'll just do int x equals 4, and typically an integer will take up 4 bytes of storage. So these next 4 boxes here will be our integer, and they'll represent 4. Now, an integer in reality is going to be represented again with ones and zeros. So each of these boxes, I'll label here, 1 box equals 8 bytes. So that means I have to represent this integer some amount of zeros. 1, 2, 3, 4, 5, 6, 7, 8, and on and on and on and on and on until we get to the binary 4 here. And there's 4 more zeros here. But I'm just going to leave it like this so you get the idea here. So different types of data types here, whether they're integers, chars, or maybe a struct that we create, which might be even larger, take up memory and RAM. Now, just looking at this representation I have of memory, you can see that there's only a finite amount of space. And intuitively, that makes sense as well, because if you think about your machines, well, you can't store unlimited data, right? There is a limit. That's why sometimes you upgrade your machine, or these green sticks that I was referring to, known as RAM, which are your working memory. So that means this resource, again, is finite. So this is a finite resource. And most programming languages, if you've programmed before in, say, Python or JavaScript or even Java, do a pretty good job of just managing this resource for you. But in C, we actually have a little bit of control over how this memory is used and how things are allocated. So let's go ahead and just look at a simple example, and we're going to be refreshing a topic that we talked about previously known as block scope. And I'll take a few notes down here so we can keep a reminder of what's going on. So let's just go ahead and create an example here. I'm going to create just a file called main.c. I'll make it a little bit bigger so you can see it. And we have the entry point into our program. That's the main. We return a value here. And maybe we include some libraries, which essentially does this copy and paste of a bunch of standard input output functions that we might use, like things like printf and so on. Okay, so now that we've got that settled, let's go ahead and write a function here. And I'm just going to call this function foo, which is sort of an abbreviation programmers will sometimes use to just have a function as a example. It's sort of like lorem ipsum if you've ever done graphic design or layout. It's just a placeholder here. So recall that if I create some variable here, foo here, and within main here, if I have another variable called x, this is legal. In fact, I'll just go ahead and compile this just so that you can see, and we'll give this an output here, that this is allowed. I'm allowed to have this same name symbol here, x equals 4 here, x equals 4. They're both integers, but the scope at which I use this variable is within this curly brace and this curly brace, just like x exists within this main function here. So again, another way that we refer to these things, we talk about this as sort of block scope, but this is just a local variable, meaning that it's only available within the main function or foo. Now, to avoid some confusion, I'll just go ahead and give these different names, like a here and x. They're essentially arbitrary here. Now, why are we able to get away with this? Well, remember, whenever we call some function here, we are in a different scope, okay? And we are just temporarily creating this variable here, and then I've previously said it just goes away. And in fact, it's actually really important that this memory here can be reclaimed, because recall, even one integer here takes 4 boxes of our precious memory in RAM. So what would happen if I did something like this? I'm going to create a for loop for I, while I is less than something really big, say 1 million, I++, and I'll keep calling this function foo here. Okay, and let me get rid of my local variable here. Now, if I call this 1,000,000 times, if we didn't reclaim this memory somehow, then, well, we'd be using, again, a lot of our precious RAM over here. So it makes sense that we erase or get rid of this memory each time we call the function. So I'm just going to run this program just so you can see that my computer doesn't crash or catch on fire or anything. In fact, it executes quite quickly. So hopefully that's at least a little motivation that when we store stuff in variables, depending on what the value is, if it's a float, a character string, integers, doubles, it doesn't matter. The memory will be reclaimed within the block scope for whatever this name symbol is or this variable. So that's very important. And what we have here, again, is this idea with block scope. Our local variables are reclaimed in the scope, the block scope. The block scope, they are initialized in. Okay, so that's the idea here. Every time we call foo, this variable will be created, and then when we hit this right curly brace, it will be reclaimed or removed from memory. Okay, so how exactly does this work here? Well, for this, I want to introduce something known as the stack. So let me go ahead and get rid of this little diagram here and discuss what the stack is. So actually, I'm going to need a little bit more room here just to make sure we have plenty of room here. And the stack is in C a reserved place of memory for our functions to execute and store data. So it's some sort of working memory for us per program that we're running where we can freely allocate variables and then those variables will be reclaimed for us. Okay, so what does this stack mean? And I'll go ahead and write, this has to do with stack-based memory allocation. Because that's what we're doing here. We're allocating enough memory for some integer. We're naming it A and storing the value 4 inside of it. Okay, so I've used a few different terms here. One is just this idea of a process that's running. That's this thing here, prog. It's the active program that's running. We could run this program 500 times, just like the equivalent of many folks have 500 Google Chrome or tabs open. That's 500 of the same process running essentially. So we have per process that's running, and I'm going to represent this in a sort of data structure here, or there's just this diagram where I have our program here that's this thing here when it gets compiled. We have some of the source code, which I'm just going to label the text here. Then we have some other regions of memory for this actual program here that gets compiled as the ones and zeros, some things like read-only data and these kind of things, which we're not worried about. And then we have a section of memory here, which I'm going to refer to later. And then we have this memory at the top here, which I'm going to call the stack, and I'll label it right here. So this is the stack. And this is exactly the topic that we're talking about today here with the stack-based memory. So per program that's running here, again, we have a finite amount of resources where I can store things like A equals 4. Or perhaps in this function here, if I allocate something else like B, I say B equals 7, that also gets stored on the stack here. And let's go ahead and just create another integer here, C equals 10, and C equals 10 here. This is on the stack. And I'll sort of divide these up because these are individual regions of memory here. And then what happens, again, when I leave this function here, is the stack is cleared. So our stack memory goes away. So I'll just erase all of these things that I had here, and it goes away. So that is how local variables are essentially stored. They're pushed onto the stack. So we have this term, push, which means to add to the top of our stack. And this term, pop, which means to remove from top of the stack. Now there's something a little bit weird here in how to actually represent this accurately. Our stack actually is growing this direction, so the top would be somewhere here. So in our example, when we add A first, this is the top of our stack, and then we add B, and then we add C, and so on. So it's actually growing downward until we hit this region here, which is the end of our stack here. If we go over this, we get a stack overflow. Okay, so if I were, for instance, to allocate 1 million integers here, and I just spent a lot of time typing out each of these individual integers, we would overflow into these other regions of the memory that's been allocated for this single program, and that's where the name Stack Overflow comes from, our favorite website. Well, second favorite after this channel, right? All right, anyway, so that's the basic idea of a stack-based allocation. So data is temporarily pushed onto this stack. That's what I've shown over here. And then it's popped. So again, I'll just pop everything off the stack when we're done with our function call. And in fact, this is an important mechanism because what if I have something like this here? And I'm going to create another function here, bar, which is another one of these just temporary functions programmers like to use. And I'll call bar here. And I'll have some other integer here, d, for example. And let's make sure this all fits on the screen so you can see. Now, this is a legal program. I'm going to compile it. That doesn't really do anything useful, but I want to show you how when I call foo here, memory is allocated and deallocated on the stack. So first we call foo, which is going to, and usually you have the actual function. For now, I'm going to represent with a name, but it's the address of where that function is. That's how my program actually knows to return back to line 20. Or actually, let me get rid of this loop just to make things simple here. But how does my program actually know to come to, after we're done executing foo here, to move now down to line 19 and then eventually 20, well, we store the address of foo, and this is the return address from which it was called. So I'm going to say this is just the return address. And then we store our local variables, A, B, and so on. Actually, let me be a little bit more precise about the order. Depends on the sort of calling convention here, but we'll actually store the locals first, A, B, C, and then our return address of foo. But before we're done with foo here, we're actually maybe going to have other data here, like our parameters. So let's give ourselves a parameter. I'm just going to call this X here. So that would also have to be temporarily stored on the call stack, something like X here. And remember, that's why in C, we do this thing called pass by value. So we're making copies of something, which are just temporary values that are stored on the stack here. So this X here, I'm going to draw an arrow over to this X here that I'm highlighting on the left side. That's stored on the stack. That's why we have just a temporary copy that we're actually working with. That's why in our previous lessons, when we learned about pass by value, this X here, that is this parameter here, since it's stored on the stack, is not something that when we modify, the value changes. If it's just a regular variable here. If it's a pointer, it stores an actual address somewhere else. But we're building some intuition here. All right, so what else do we have? Well, as soon as we get to, we've stored everything here, and then we have a function call. So we haven't hit this right curly brace yet, which would otherwise indicate that we want to clear everything from the stack. So everything here stays on the stack, A, B, C, foo, which is our return address. Or in other words, that's telling us, hey, go to line 19 when you're done executing here. So we'll go over here. That's what we're storing there. And then we have our parameters here. And then we have bar, which we store, I'll add another line here, the integer D, and then just a really thin line here. Then we have our return address of bar here. So that's what I'm writing here. In fact, let me just draw an arrow so it's a little bit clearer what I'm writing here. Bar return address. Okay, now why am I storing this? Well, after I'm done executing bar here, I know that I need to return back to the end of line 8 and, well, whatever follows it, which here is line 9, and then clear the rest of our stack here. So in C, that's how stack-based memory allocation works. Our variables that we create, our locals, are cleared from the stack. They're stored on the stack as we allocate them, and then cleared when we're done with that function. And we also need to store some other information like where do we return to so that we know where to continue executing our code, and the arguments that are passed in, which are passed in by copy, or we call pass by value, are also stack allocated, and then the memory can be reclaimed. All right, so this is maybe most of what you need to know, at least when you're starting off writing some C programs. But you might ask yourself a question and say, well, Mike, what if I don't want stuff to be automatically reclaimed? You said the C programming language was very powerful. We got to control how memory works. And that's true. And that's what this region that we still have to talk about here. What is all this empty space here? It is space. It is memory where we can store things. And I'm going to just separate this out here. And this is called heap memory. Now, memory that's on the heap, and you can think of the heap as this big collection of memory where we can allocate and store lots of information. So I'll sort of put a box here and say large storage. And it's for variables and data structures that are going to be long-lived. Long-lived memory. And we allocate and free this memory. So This is what is heap memory, and that gets stored somewhere in this region. Or rather, this is the sort of collection that might expand or decrease based off of how many allocations that we do. So for heap memory, let's go ahead and look at an example so you can see exactly what it is here. So what I'm going to go ahead and do is clear some of this code here, our stack, and I'm going to include a library here, the standard lib for h here. And just momentarily, I'll open up another terminal window here, and I'm going to make this font big, and I'm going to look at the function malloc. Now we've looked at this function previously, in fact, in one of our first days of C, to see what this is. And this is a memory allocating function here, which basically goes to the operating system and says, hey, I need some resources. Can you give me some resources and store them in this heap or the working memory, and don't free that memory until I explicitly tell you to. So that's the idea of malloc here. And I'll go ahead and open this so you can see how it works. Now malloc is used in conjunction with the function free, and free is what we use to explicitly free some memory. Okay, so with that said, you can use the manual pages to look at these functions, but I'll go ahead and close out this terminal, and let's look at an example of some long-lived memory. So first, in the main function here, let's go ahead and create some memory here using the malloc function. So malloc itself, and actually let me open this up again so we can see, takes in the size of the memory that we would like. So how many bytes? So again, you could just pass in a number here. Typically, we'll use something like the size of and say integers, and then how many do we want? So an integer typically is 4 bytes, and let's say we want 50,000 of them, okay? And remember, this heap is big, so that means that we can store lots of data. On our stack, if we store 50,000 of something, that might be actually too big for our stack, and then we get that stack overflow. Okay. So what do we do here when we're doing malloc here? We've allocated the size or the number of bytes, and it returns this void star thing. Now, void star is a little bit weird. We've seen void in terms of functions previously, meaning that there's no return type. But void star, when we see it, actually means a void star like this, which is a pointer that we're returning. So if we're returning a pointer and we have void, void just means any data type, because we don't know that we're returning integers here, so we have to specify. So if I'm working with integers here, I'll just create a pointer to some integers here, and then malloc I'll cast explicitly to say, well, we didn't know what the type was. Remember, void star is just this sort of catch-all. It could be a block of memory to integers, to floats, to doubles, to custom data type. We don't know. So I'm casting it here explicitly because that's how many bytes we're getting. And then we'll treat this as a pointer to a block of integers here, 50,000 of them. Okay, so that's the idea we call malloc here. So let me go ahead and illustrate malloc in our diagram. And as soon as I malloc, and let's do the 50,000 times size, the size of the integer, size of int here. And again, what that's going to do is this time in this heap memory here is allocate a block somewhere in our operating system of these 50,000 integers here. So we could just imagine this is 50,000 integers, and we get a pointer to the start of that block, whether it's 50,000 items or just one integer, and however many bytes it is to represent that. Now, if I've allocated this memory here, again, this is long-lived memory. So it's going to live until we say to free this memory. So in fact, I have to free this memory here by calling free array here. And then that's what will actually deallocate or erase our memory in the heap. Okay, so malloc and free are used in conjunction. Now, why is this useful? How do I make this long-lived? Because the example I've used here, essentially I've just malloced and freed within the same block scope. So let's go ahead and write an example where we malloc in a different function some collection of data and then free it elsewhere. So what I'm going to go ahead and do is move this allocation to another function I'll call allocate on heap, and we will return a pointer here. So we'll return our actual array. Okay, so if I call this function here, and let's get rid of the bar. Let's go ahead and call allocate on heap. That's going to return a pointer. So I need to assign it here in star heap data. And then I'll actually free my heap data in the main function here. And let's actually do something with this array just so it's interesting. For int I, let's reduce the size just a little bit, maybe to just 10 items, just so that it's a little bit easier to see what's going on. But we'll just assign each of these items here, return it, and then we'll do something here as well by just printing off the data here. So let's do a printf heap data at some index I. So I'll use %d for that, equals, and then whatever the value happens to be here. So I, and then heap data at our index I. Okay, so let me go ahead and leave this open. Let's go ahead and see what this program does and see how we've utilized the heap here. So I'll go ahead and run this program here. Oops, let's see, made a little mistake here. Looks like we don't really need an argument here. Actually, let's make this the size here, just to make it a little bit more interesting and make our program a little bit more dynamic here. So let's go ahead and just take in the size, and we'll pass in, well, let's just make a variable here, the size. And then we can be consistent here. And this is a nice program to walk through and again, just show you the purpose here. Okay, so I'll go ahead and compile that. Let's go ahead and run this. And I'll need to make this window a little bit bigger here. And we'll see that, well, we have this heap data here, and we stored some values in 0 through 9 for the size of our heap data here. And it is, in fact, giving us the values here that we've set up here. So again, the observations to make and sort of the point of this lesson is we can allocate memory that's going to be long-lived on the heap. I've allocated it in this separate function here, assign the memory, and then I return a pointer to some memory that lives in the heap. And because that memory lives in the heap, then when I leave this scope, when I return from this function, in other words, at line 12, this local variable itself, array, might go away. But the actual memory that we've allocated will in fact live on forever. So that's an important distinguishment. This is what's living on forever, this chunk of memory that we've allocated. This pointer is sort of a temporary pointer to the front of that block here. And we return that address, which is the start of our block of however big the memory is. Okay. And then what we do is in our program, after we've allocated 10 integers here, so size 10 times however big an integer is, 40 bytes if you think about it in bytes. Then we go ahead and say, hey, give me another, just a local variable here, just something to temporarily point to that block so that we can access it. And then we're just going to use this as heap data here. And well, this is just a regular sort of dynamic array, meaning that we've heap allocated however big we want, so it's dynamically sized. We see the actual values that we used before. It's pointing to the same block of memory. In fact, it'll be useful for us to actually see where this lives in heap. So let's just go ahead and print off the array. Let's say heap memory address. And we find out addresses with %p. And array is our pointer. So we'll just go ahead and leave that as is. And I just want to go ahead and show where the heap data is. And let's go ahead and see what the result is. So by running this program, you can see the heap memory address, the thing that we've allocated somewhere on our operating system using this malloc function, which magically returns the address, that we have this address here. And then later on, when we've returned that address here, well, it's still the same address in the heap, wherever this happens to be. And it might be important or interesting to actually look at the address of this local variable here, array. So let me show you the stack memory of a local. So that is ampersand array. And let's go ahead and do the stack memory of a local, and this time the heap data. Okay, so I'll go ahead and run this program. And what we're going to see is, again, our heap addresses are the same, but our local memory here is in fact quite different here. You'll see that these two variables here, the first one I print out, the heap memory address, that's this one, ends in 240, 1240, etc. And this one, the stack memory of the address of just heap data, which is just this local variable, is 1270. So clearly different addresses. And they're sort of in similar locations. You can see that one starts off with 0x7ff for both of our stack, because again, if we have our stack, things are relatively close in location. So it makes sense that their addresses would be similar. And then our heap memory is 0x56, something wildly different. That's because our heap's all the way over here on this part of our code, and our stack's all the way over here. So there is some sort of distance you can observe here on stack-based memory versus the heap-based memory. All right, folks. So just to summarize again this lesson, we can see that there is some difference here, stack versus heap. That's the number one important thing that you should come away from here. Stack being automatically allocated and clearing out the memory when you leave scope, and heap, again, being long-lived and you must use free to get rid of it. Okay, and this also shows why we need things like pointers in the language, so we can point to chunks of memory, whether they're in the heap. We can also point to things in the stack, but that's kind of dangerous because, well, these things are only temporary. So if we have a pointer that points to a specific box here, and this memory gets cleared away, then we don't really know what's in a box here. Okay, so just a warning on that. Okay, so let's go ahead and wrap things up here. So this lesson's been quite a big one here. We've talked about how memory is managed in the C language, and we have stacked based, which is automatic, and heap based when we know we want some memory to live for a long time and we want to manage it ourselves. And it's really important for us to think about this. As the example I gave, for example, if you have a pointer to a stack based memory location, that's going to disappear over some time. So that's one thing to actually be careful about. And otherwise, we like having these heap-based allocations because let's say that we're building some sort of data structure. And in fact, that's what our next day in C, we're going to be talking about building data structures. But the idea is that we have control over how long that data stays in memory. Okay, so that's a really, really powerful idea. So all right, folks, I hope that was a useful lesson and you understand a little bit more about memory allocation in the C programming language. And at the least that there is a difference between stack-based allocation and heap-based allocation. That is memory that's going to be long-lived on the heap where you malloc and free, and short-lived on the stack where you don't have to do anything and the memory is allocated and reclaimed for you automatically when you go out of the curly brace scope. So now that you know this, you're now armed with some important information in the C programming language. And you're also starting to think a little bit like a systems programmer, thinking about memory, where it's stored, and how it's actually working on the stack. And it's kind of cool because then you sort of start to understand how the machine's actually working. So you're one step closer with understanding how things really work and how the magic works by programming in the C language, which again is a really cool motivation of programming in C. So folks, if you enjoyed this lesson or anything was unclear, just let me know, comment below, and make sure that you like and subscribe so that you don't miss the next lesson in this series and hopefully gain even more valuable C programming knowledge. We'll see you in the next one, folks. Take care.